With this lesson, we are going to talk about the measurement of magnetic properties of materials by means of magnetometers. The term magnetometers encompasses equipment that can do many different things. They usually can be grouped into two categories, those meant for measuring magnetic fields and those meant for measuring the magnetic properties of matter. In this lesson, we will not talk about the equipment to measure magnetic fields, and instead we will focus on instruments that are meant to characterize magnetic materials. We are going to focus our attention even more to just the magnetometers that are called static. This means that they measure the magnetic properties of matter while the magnetic field is kept constant over time. This does not mean that the magnetic field cannot be varied. So, what does static really mean? It means that the magnetic field does not vary during the measurement of the magnetic property of interest. Of course, you can change the magnetic field value and measure the magnetic property as many times as you want at different applied field values. And yet, this is not always true, as we will see later on. The physical property that you want to obtain for your samples is the magnetization. Unfortunately, a magnetometer does not measure magnetization directly. Instead, it measures a magnetic moment. As you recall, a magnetic moment is the extensive quantity, whereas magnetization is intensive. That means that if you want to obtain magnetization, you must take the magnetic moment that you measure and divide it by the sample volume. We will see later on that obtaining the sample volume may not be trivial at all. The magnetic moment of your sample depends on a lot of different external quantities. Of course, there is the magnetic field at which the sample is emitted, but it also depends on the temperature. Usually you can be interested in measuring the magnetic moment from just a few Kelvin to maybe even more than 1000 Kelvin. Then it can depend over time, with the time constants that can range from a few seconds or even fraction of a second to even days. Then, depending on the shape and the anisotropy of your sample, it can depend on the orientation of the sample itself with respect to the applied field, and maybe even more quantities. Magnetometers usually are able to measure the magnetic moment as a function of at least one of these quantities, maybe even more than one. What are the typical samples that are characterized with such kind of magnetometers? Of course, they are magnetic materials, but they are in the form of thin films, for example, or nanowires, or nanoparticles, or patterned media, or porous materials, but also bulk samples, provided that they are not too heavy. A magnetometer consists of three mandatory components, plus additional ones that are optional. The first mandatory component is a means of generating a magnetic field of the intensity that you want, and that allows also the possibility to change the magnetic field value. The second component is a means of measuring the magnetic field that you are generating and at which the sample is submitted. The third mandatory component is a means of measuring the scalar or vector magnetic moment of the sample. Additionally, there can be as many components that you want that are able to measure or control any additional quantity that can affect the magnetic moment that you measure, for example, the temperature, the angle, and so on. To generate the magnetic field, you have three options. The first is to use electromagnets. They are very versatile. They can easily overcome an applied field value of 2 Tesla. They can even reach almost 3 Tesla in many cases. Their problem is that they are non-linear, so you need a closed-loop feedback in order to be able to control adequately the applied field value. A simpler solution is to use Helmholtz coils. They are linear, so you calibrate them once and do not need to worry about them anymore. but they are severely limited in the maximum field that you can apply, that can go up to a few millitesla, no more than that. If you really need huge field values, in any case less than 20 Tesla, because we are talking about static fields, your only option is superconducting solenoids, which are almost linear, but that almost is very tricky because they suffer from some hysteresis that you need to take into account. Let's have a closer look at each of the three systems for generating magnetic fields, and let's begin with electromagnets. As you can see in the graph, if you measure the current that flows in the windings of the electromagnet, you can see that the magnetic field is not proportional to the current. There is a nonlinearity. This nonlinearity comes from the fact that the magnetic material that makes the electromagnet is nonlinear. Unfortunately, you cannot simply take into account this nonlinearity through calibration, because the magnetic material that constitutes the electromagnet also displays hysteresis, so you cannot simply measure the current and know the applied field values. Instead, you must measure directly the magnetic field that is present in the gap of the electromagnet. To do that, you need a gauge meter and normally a Hall probe. Helmholtz coils are much easier to deal with because they are linear. So you just need to know the current that flows through the windings in order to know the applied magnetic field. Of course, this is true only if the temperature is kept sufficiently constant. You also need to know the calibration factor of the coils, because you must be able to convert the applied current or the driving voltage into a magnetic field. But this calibration can be done once for all. The only equipment that you need after calibration to know the applied field value is a multimeter to measure either the voltage or the current used to drive the coils. Superconducting solenoids are just coils, so in principle there's not much more to be said about them. You calibrate them, and then you just measure the current that flows through them in order to know the applied magnetic field. The problem is that they are not exactly linear because they display some hysteresis, and this will be the subject of a discussion later on. Now, as we said, we would like to measure the magnetic moment of our samples. A common approach is to use a VSM, a vibrating sample magnetometer. It consists mainly of three parts. One is the electromagnet, that is the light blue part in the schematic diagram, with its Hall probe to measure the applied field value. The second part, that is the light orange part, is the so-called vibrating head. It is a linear motor. In its simpler form, it is just a loudspeaker. Maybe it can be a little bit more complex. It is a linear motor. That means that it puts the sample in vibration along the vertical direction, up and down, at a fixed frequency and at a fixed amplitude. The sample is glued in some way at the end of a rod. One edge is attached to the vibrating head. The other edge is left free in the middle of the gap of the magnet, where the sample can vibrate up and down. It vibrates up and down in close proximity to the third component, that are the pickup coils, that are meant to measure the magnetic moment of the sample. How can a VSM measure the magnetic moment of the sample? Through the Faraday-Neumann-Lenz law, the law of induction. You have a magnetized object, your sample, that moves with respect to copper coils. Since it moves, there's a time variation of the linked magnetic flux in the coils, and this flux variation induces a voltage in the coils. You measure this voltage, and through suitable calibration you know the magnetic moment. Why? Because the output of the coils is a function of the frequency of vibration. This is controlled by the system through the vibrating head. The amplitude of vibration, which is again controlled through the vibrating head, the magnetic moment of your sample, which is the unknown, but unfortunately also the position of the sample with respect to the coils. This is the reason why VSMs are normally equipped with knobs that allow to move the sample within the gap of the electromagnet in order to find its optimal position. Let's start discussing the position along the Z direction, the vertical one. Let's assume that the sample is very far away from the gap of the magnet, so also far away from the pickup coils. The signal that they will measure is close to zero. Then you approach along the Z direction the pickup coils and the signal increases. If you go beyond the middle of the gap and start to again move far away from the pickup coils, the signal will decrease again and approach zero. So your optimum sample position along the Z direction is where you have the maximum reading of magnetic moment of voltage, if you want, from the coils as a function of the Z position. The same way of reasoning applies along the Y direction. If your sample is too far away from the coils, the signal will be zero, whereas it has a maximum when the sample is in the middle of the gap. The reasoning is the opposite when you talk about the X direction, that is the direction of application of magnetic field, because the signal that is picked up from the coils is a maximum when the sample is very close to the either right coils or left coils, because there is an overcompensation given by the coils that are closer to the sample with respect to the ones that are more far away. So the signal will be minimum when the sample is in the middle of the gap. Positioning of the sample is therefore done by moving the sample along the Z, Y, and X directions, trying to find the respectively maximum and minimum reading of voltage or magnetic moment from the coils in a repeated way, recursively, until a stable position is found. In that position, you are ready to do the measurement. So to sum up, the vibrating head is responsible for keeping the frequency and the amplitude of vibration constant over time. The user is responsible for adjusting the position of the sample along the X, Y, and Z directions according to the rules that we discussed a few moments ago. Then the first thing that you must do is to calibrate the system. To do that, you insert a sample of known magnetic moment, you measure the voltage coming from the pickup coils, and use the ratio voltage over magnetic moment to know the calibration factor. Now you can replace the calibrating sample and put your own sample that is unknown and measure the voltage and convert it into a magnetic moment for all the applied field values that you want. Remember when we said that we are talking about static magnetometers, the magnetic field is constant during the measurement of the magnetic moment for each point of measurement of magnetic moment. Then you can change the applied field value and measure again the magnetic moment in the same position of the sample with the same frequency and same amplitude. Point by point, you end up measuring a magnetization curve, for example, a hysteresis loop as shown in the figure. A different kind of magnetometer, less common than the VSM but still worth discussing, is the so-called AGFM, alternating gradient field magnetometer. It uses the same way to generate the magnetic field, so an electromagnet and a Hall probe to measure the applied magnetic field. The difference is in the way of measuring the magnetic moment of the sample. In the case of an AGFM, the sample is glued in some way on a pad that is placed again in the middle of the gap of the magnet. The pad is mechanically connected to a piezoelectric transducer. As in the case of the VSM, the sample moves, but the reason why it moves is completely different. In the VSM, there was a linear motor that induced the movement of the sample, and there were coils that picked up the induced voltage. In the case of the AGFM, it's the other way around. There are coils that are no longer pickup coils. These are coils that are used to generate a magnetic field. In fact, these are coils that generate a gradient of magnetic field that is superimposed to the static field that is generated by the electromagnet. As you know, when your sample is submitted to a gradient field, it is also submitted to a force that moves it towards the region where the magnetic field is stronger. This movement is in fact caused by a force that is converted by the piezoelectric transducer into a voltage. If you drive the coils in such a way that the gradient is not constant over time but will oscillate over time, an alternating gradient field, then also the force at which your sample is submitted will depend over time. The piezoelectric transducer will give as an output an alternating voltage that can be used that can be amplified and used for measurement. In order to make the magnetometer as sensitive as possible, resonance conditions are chosen. So each time you measure a sample, you must first find the condition of resonance of the mechanical system through normally an automatic procedure. Once that resonance frequency is found, you can do the measurement again as with VSM. So an AGFM controls the frequency of the gradient field that you use to make the sample oscillate. It also controls, and that is the resonant frequency, it also controls the amplitude of the gradient. The user adjusts the position of the sample in the middle of the magnet, again with a similar criterion as used for the VSM. And the only quantity that remains is the magnetic moment of the sample. The ensemble of these quantities gives the output from the piezoelectric transducer, so a voltage that can be converted into a magnetic moment. How? In the same way as with the VSM. First, you calibrate the sample, the system with a sample of known magnetic moment, you find the output coming from the piezoelectric transducer, and you use that calibration factor to measure the magnetic moment of your unknown sample. The measurement is done, as in the case of VSM, point by point. You apply a magnetic field of the intensity that you want, and you measure through this technique of alternating gradient the magnetic moment of the sample. Then you change the magnetic field, measure again the magnetic moment of the sample, and point by point you end up measuring a whole magnetization curve, for example, a hysteresis loop. Then there are SQUID magnetometers, or superconducting quantum interference device magnetometers. These are similar to VSMs, because in fact, as we will see, the sample is kept in movement. But normally they use superconducting coils instead of electromagnets to generate a field. That is not mandatory, but the sensing element, the so-called SQUID junction, requires liquid helium temperatures to operate. And so using a superconducting element also to generate the field almost comes for free. So normally SQUID magnetometers use superconducting coils to overcome the maximum field limitations of the electromagnets. For the rest, the operation is similar to that of the VSMs. There's a linear motor that keeps the sample into movement, and then there are coils that pick up the induced voltage due to the fact that there is a time variation of the linked flux with the coils. The movement of the sample can be periodic, when the linear motor puts the sample into vibration, and that is really close to what a VSM does, or can be a non-periodic signal because the sample is moved from the bottom coil to the top coil and the other way around just once, and the induced signal is picked up, amplified, and integrated. The real difference with respect to a VSM is in the detection system. The voltage acquired by the pickup coils is not directly amplified, but passes through a squid junction that is a very sensitive junction that uses a quantum effect in order to measure extremely small variations of magnetic moment. That is the reason why squid magnetometers are the most sensitive among those that we are discussing in this lesson. In the end, a squid magnetometer behaves in a similar way with respect to a VSM or an AGFM. You apply the magnetic field that you want, in this case, for example, with a superconducting coil, then you move the sample either by vibration or by the so-called extraction method, as we said, from the top coil to the bottom one and the other way around just once, and then you analyze the signal that is taken by the pickup coils after having it passed through the squid junction that allows for the greatest sensitivity. The voltage is converted into a magnetic moment after calibration, which again is done using a sample of known magnetic moment. The whole magnetization curve, for example, the hysteresis loop, is acquired again 1 point at a time for all the desired applied magnetic field values. Now that we have the magnetic moment measured by the magnetometer, it's about time to figure out a way to determine the sample volume in order to be able to calculate the magnetization. Except that it's not true that what you have obtained so far is the magnetic moment of the sample. What you have measured so far is a magnetic moment that is the sum of 3 contributions. The magnetic moment of the sample, that is the final result that you want to obtain, is just one of these 3 contributions. So what are the 3 contributions that add up to form the measured magnetic moment? Well, of course, there's the magnetic moment of the sample, that is the final result that we want to obtain. Then there's the magnetic moment of the support. The support is, for example, a substrate in the case of a thin film, or the container used to put the powders or liquids in case of samples of that kind, or anything else that comes with a sample that is used to support it. It has a magnetic moment, and so it must be measured independently in order to estimate its value. And then there's the holder. The holder is, for example, in the case of a VSM, is the quartz rod that you can see in the picture in the bottom left. But not only the quartz rod, also the plastic part that is screwed into the quartz rod to hold the sample, in fact. And also, for example, the PTFE tape used to hold the sample in place. In the case of an AGFM, it is its probe, etc. Any object that mechanically connects the sample to the vibrating head in case of a VSM or to the piezoelectric transducer in case of an AGFM is the holder. It has a signal as well, and so also the signal of the holder must be measured independently. Let's make an example with a thin film, so a material that is thin enough that the background contribution of the holder and the support are not negligible. In the figure you can see the measured magnetic moment coming from the magnetometer, and you can immediately see that there's something strange because of that negative slope where you should expect saturation. In fact, that slope is not due to the film itself, but it's due to the additional contributions to the measured magnetic moment. We are not measuring the thin film alone, in fact, we are also measuring the substrate, the support, which is silicon oxide. We are measuring the PTFE tape that is used to keep the sample in place on the sample holder, and we are measuring the quartz rod altogether. So let's store the previous measurement somewhere, and now let's focus on the sample holder. So we remove the sample and we do a second measurement in the same conditions within the same field limits with the same field points, but with no sample, but we keep the quartz rod and the PTFE tape that we used previously to keep the sample in place. We repeat the measurement and, as you can see, we obtain a nice paramagnetic signal that is the contribution of the holder. Now we must determine the magnetic moment of the substrate of the film. To do that, we do a third measurement with a clean substrate with no film on top. Of course, since we are measuring magnetic moments, which are extensive quantities, we must remember that the volume of this clean substrate will not be exactly the same of the volume of the substrate that had the thin film on top. We will see how to deal that. We repeat the measurement again with a rod, again with the PTFE tape, and with this clean substrate. And what we obtain is a nice diamagnetic signal, that is the contribution of the substrate, of the support. Of course, this measurement also contains the contribution of the holder. That's the reason why, in order to obtain the magnetic moment of the clean substrate, you must subtract from this measurement the previous measurement of the holder. Finally, we must remember that the volume of the substrate of the thin film is different from the volume of the clean substrate that we used in the previous measurement. So we must rescale the magnetic moment of the clean substrate to the same volume of the substrate of the film in order to obtain its magnetic moment. If we assume that the two substrates have the same thickness since they are cut from the same wafer, it is sufficient to rescale the magnetic moments using their surface area instead of their volume. At last, we can combine everything together. We have done three measurements, one of the holder, the substrate and the film on top, one with the holder and a clean substrate without the film on top, and one of only the holder. We must measure the surface area of the two substrates, the one with the film and the one without the film, and by combining everything according to the formula shown in the bottom part of the slide, we can calculate at last the magnetic moment of the sample of the film without all the background contributions. If we plot the result, that is the black curve that you see on the graph, and as you can see, that negative slope that was so strange has disappeared. In fact, that was due to the background contributions. Now the black curve is really the magnetic moment of the sample. Now that we have the magnetic moment of the sample, we can finally try to determine its magnetization. To do that, we need to know the volume of the sample. This operation may not be trivial, and it really depends on the kind of sample that you have. For example, you can try to obtain the sample volume directly, or to measure mass and density, or to measure surface area and thickness, or any other relevant means depending on the sample type. Let's make a few examples. Let's say you have a thin film. In that case, measuring the surface area is rather easy by optical means, normally with a photograph or with an optical microscope. You must have a different way to measure thickness with a profilometer, an AFM, something else. You can obtain this way the volume by multiplying the surface area and the thickness, but keep in mind that the film density might not be the same as the bulk density. For thin films, sometimes you can also weight the substrate before and after the deposition. This works in a few cases. You don't have the volume in that case, but at least you have a mass. Films may not be continuous, they can be patterned media. In that case, using either images taken with a microscope or the nominal shape of the pattern that you are putting on the film, you must define a covering ratio. But also keep in mind that in order for that covering ratio to be effective, the surface must be homogeneously covered. Different is the case of powders. Normally, weighting them, measuring their mass, is the easiest approach, but that does not give you a volume, only a mass. In any case, be very careful to specify what the volume of the mass that you have measured refers to. For example, let's say that you have iron oxide nanoparticles, magnetite nanoparticles, coated with silica. The mass or the volume that you have measured refers to what? Refers to magnetite or to the whole magnetite plus silica shell system? Or let's take another example, a multilayer system, a cobalt iron boron film that has a top layer and bottom layer of tantalum. The volume or the mass that you have measured, is that of the whole stack or only of the cobalt iron boron layer? Of course, the answer depends on what you have measured, how you have measured it, and if you have a way to subtract the contribution of the component that is not magnetic, just the silica shell in the example of particles, or the tantalum layers in the case of the stack. The answer is not all the time the same. It really depends on what are your possibilities. Another serious issue of measurements done with magnetometers is that the sample is in the so-called open magnetic circuit configuration. That configuration is depicted in the sketch on the bottom left. The sample has an air gap within its faces and the poles of the magnet. The situation is opposed to the case of the flux closure, where the sample is clamped between the poles of a yoke. There is no gap. What is the difference? What's the effect of this gap? The effect is that on the faces of the sample in the open magnetic circuit configuration, you have the development of magnetic poles. This means that the sample is immersed in the applied magnetic field, and that is the field that you measure with the, for example, Hall probe of your magnetometer. But the magnetic field that actually magnetizes the sample inside is not the applied magnetic field, is the applied magnetic field plus the so-called demagnetizing field. The demagnetizing field is a field that originates inside the sample from the free poles that develop at the two sample sites. These free poles are not there in the case of flux closure, but in the case of open magnetic circuit configuration, the poles are there, and so also the magnetizing field is there. So if you really want to know what is the so-called internal field, the field that the magnetic material is sensing when submitted to the measurement, you must correct the applied field by the demagnetizing field. What is the problem? The problem is that the demagnetizing field is not trivial to know. It depends on the magnetization of the sample, and it also depends on the sample shape. So in this equation, you can relatively easily know the applied field, but determining the demagnetizing field in order to calculate the internal field, the field that is actually acting on the magnetic material, is not trivial. The demagnetizing field can be calculated exactly only for ellipsoidal samples. For all the other shapes, there is no analytical formula to calculate the magnetizing field, and you must use numerical approaches to calculate that. However, as a general rule, we can say that the magnetizing field is proportional to the magnetization through three coefficients along the three main directions in space. And these coefficients sum up to unity, at least in the SI system. And in general, coefficients along the three directions are larger along the directions where the sample is shorter. Clearly, in the case of a sphere that is isotropic along the three directions, the three coefficients have the same value, which is 1/3. Another interesting case is that of thin films, where typically the thickness is much smaller than the lateral dimensions. So if we say that the z direction is the one perpendicular to the surface, so the one along the thickness, we can assume that the coefficient along z is practically equal to 1, whereas the other two coefficients are practically equal to 0. Let's examine a practical example. We take a spherical sample, that is an yttrium iron garnet sphere that is used to calibrate the AGFM. In the graph on the left, you can see the magnetic moment as measured by the AGFM. The curve is a function of the applied magnetic field. In the right graph, we are correcting for the holder, substrate, etc. Contributions so that we can obtain a magnetization normalized to the sample mass. Now we use the nominal yttrium iron garnet density to convert the mass into a volume so that we can have the magnetization normalized to volume as a function of the applied magnetic field. Now, since most magnetometers give results in units that are not SI, we convert the units into SI, so the magnetization in Tesla and the applied magnetic field in ampere per meter. Now we are ready for the last step. The magnetization is in Tesla, the sample is a sphere, so we know how to calculate the magnetizing field as 1/3 of the magnetization. We can therefore calculate the internal field as the applied field minus the magnetization field, and plot the magnetization as a function of the internal field. In the graph, you can see the comparison of the black curve, the original magnetization curve, versus applied field, and of the blue curve, the magnetization versus the internal field. As you can see, the correction for the demagnetized field has changed the shape of the magnetization curve that now is much more rectangular. Unfortunately, if you magnify close to the origin, you can see that there is a sort of overcompensation effect. That means that the magnetizing field that we have calculated is too strong. It should be smaller. That is due to the fact that it's not so easy to calculate the magnetizing field, because in principle the formula HD equal to coefficient times m is only valid when the material is saturated. As soon as you are leaving the saturated state, that formula is no longer perfectly valid, and you must revert to numerical methods in order to have a better estimate of the magnetizing field. Another difficulty may arise when measuring soft magnetic materials with such magnetometers. Here's an example of the same sample, an iron, copper, niobium, silicon boron thin film, which is relatively soft, measured in the same configuration. The field is applied in the sample plane along a specific direction with two different magnetometers, a VSM and an AGFM. In spite of the sample being the same exactly in the same conditions, as you can see, the loops have different shape. Why is that happening? As you may recall, in the beginning we said that these magnetometers are static. That means that the magnetization is measured during a lapse of time when the magnetic field is constant. But we also said that that is not exactly true, at least not in all cases. Indeed, that's the problem of the AGFM. The magnetic field is not constant during the time of the measurement. Why? Because, as we have seen, the AGFM superimposes an alternating magnetic gradient to the static applied magnetic field. Now, is that gradient sufficient to affect the measurement? In the case of soft magnetic materials, the answer is yes. In this case, for example, the coercivity of the sample, according to the VSM, is of the order of 2.6 millitesla. For the AGFM, across the sample size that is approximately 3 mm, the applied field oscillates with an amplitude of approximately 3-4 millitesla around the DC field value. This means that in the AGFM, the sample is not in homogeneous field conditions, and parts of it pass across coercivity during the measurement. So, this is the reason why the two hysteresis loops measured with the VSM and with the AGFM do not look the same. As expected then, the hysteresis loop measured with the AGFM is softer than that measured with the VSM. This is a typical artifact that the AGFM introduces when measuring soft magnetic materials. So far, we have assumed that when we plot a magnetization curve as a function of field, we know that field value, because we have measured it some way. Indeed, when you have an electromagnet, we said that normally we use a whole probe connected to a Gauss meter in order to know the value of the applied magnetic field. Then there's the problem of the internal field, but that's a different story, as we discussed earlier. If your magnetometer has coils, thanks to the linearity and lack of hysteresis, it is not required to have a whole probe to measure the field. However, that is still possible. You can simply measure the current that is flowing in the wires of the coils, provided that you know the calibration factor of the coil. The problem becomes more complex when you use superconducting solenoids, because they are quasi-linear but not perfectly linear, and they display hysteresis. And in spite of that, the magnetic field is still indirectly measured with an ammeter, so you measure the current flowing in the coil, and not directly the magnetic field, mostly because there are almost no hole probes that are capable of doing magnetic field measurements at cryogenic temperatures. We will see quickly why this is going to be a big problem. Let's take our squid magnetometer, which has a superconducting solenoid. Our sample is not a magnetic material, it is a palladium sample, which is paramagnetic, so the expected magnetization curve is a straight line. Strictly speaking, it should be a Langevin curve, but up to a few Tesla of applied field, it's still a straight line. So let's put the sample in the squid and measure it as a function of field. We expect the magnetization curve to be a straight line. And yes, apparently it is a nice straight line. But is it really a straight line? If you magnify enough your measured curve, you will see that it has a hysteresis, which for a paramagnetic material it is already a bad piece of news. But the real problem is that this hysteresis is even reversed. It means that apparently if you run through that loop, instead of losing energy, you produce energy. So you are violating the thermodynamic principle, second thermodynamic principle. There's definitely something that is not going on as you expect here. The explanation is not in the palladium sample, which is paramagnetic and is doing perfectly its job. The explanation is in the superconducting coil, which unfortunately displays hysteresis. When you apply a current to the superconducting coil, it generates a certain magnetic field. But when you remove that current, it doesn't mean that a zero current measured by an ammeter means that the zero current is in fact circulating in the superconducting coil. It can trap flux that opposes the applied field. And it means that even when you are not providing through a power supply any current to the coil, there can still be some current circulating in it. So the actual field value that is applied is the one calculated through the current measured by the ammeter minus the opposing trapped flux. This means that you cannot trust the reading of the ammeter, but you have no way to measure the opposing trapped flux. Since the aim of having a magnetometer is to characterize magnetic material, the problem of the hysteresis of the superconducting coil that is visible when you try to characterize a paramagnet like palladium seems to be of relatively little importance. But very often, with such kind of magnetometers, you would like to characterize materials that are super paramagnetic, like, for example, magnetite nanoparticles. Super paramagnetism means that the hysteresis curve should display several different properties that scale with a certain law with temperature, etc., but the first fingerprint is that the magnetization curve displays no hysteresis. This is more or less what you see with the red curve in the graph to the right. It really seems that the nanoparticles are superparamagnetic. But if you magnify the curve again, you see that you display some hysteresis, and that hysteresis is again reversed. So, once more, you are looking at the hysteresis effect of the superconducting magnet. Fortunately, since you have the palladium sample that you can use to calibrate the squid, you can also use that palladium sample to compensate for the hysteresis of the superconducting solenoid. Indeed, you measure the hysteresis of the superconducting solenoid through the palladium sample and use that information to correct the hysteresis, so it means that you correct the field value that you put in the abscissa of your graph. It is no longer the field that is measured through the ammeter, but it's that minus the correction that you have measured through the palladium sample. The result is the blue curve applied to the magnetite nanoparticles that this time shows a very nice compensation for the hysteresis of the superconducting coil, and the particles really look superparamagnetic at this time. In the beginning, we said that with electromagnets you can normally reach fields of approximately 2 Tesla, and in some configurations you can even go up to 3 Tesla or even a little bit more. So it seems reasonable, a good idea, that if you have enough power in your power supply, you can try to apply the maximum field that you have available in order to do the characterization of your magnetic material. Unfortunately, when doing that, when you go beyond approximately 1.7, 1.8 Tesla, there's a strange artifact appearing in your magnetization curve, which seems without explanation. When you consider an electromagnet, you normally assume that its purpose is to generate a field which is used to magnetize your sample. But also the electromagnet is made of magnetic materials, and your sample is generating a magnetic field through its magnetization. The magnetic field generated by the sample perturbs the state of the magnetic material of the electromagnet. The result is a sort of mirror effect. It is as if inside the electromagnet there were another sample with the same magnetic moment but satisfying certain symmetry conditions. Unfortunately, this mirror effect depends on the relative magnetic permeability of the material of the magnet. So, when you start approaching the saturation of the magnetic material of the magnet, its relative magnetic permeability is no longer constant. It goes close to 1 to unity. It can be shown by calculation that in these conditions, the mirror magnetic moment, the image magnetic moment, uh, goes asymptotically to 0. So when you do the measurement of your sample with your magnetometer using an electromagnet, when you approach the saturation of the magnetic material of the magnet, it is as if the magnetic moment that you are measuring were smaller. And that's the reason why you see that artifact in the magnetization curve when you go beyond 1.7, 1.8 Tesla. Unfortunately, this effect is difficult to compensate by calibration because the exact dependence of the image magnetic moment on field depends on the shape of the sample. And so unless you have a calibrant of known magnetic moment that has exactly the same shape and size of your unknown sample, the compensation through calibration is not possible. In the beginning, we discussed that with these magnetometers it is important to put the sample in the correct position at the center of the magnet, and also with respect to the coils that are used to pick the signal, to pick up the signal. Most magnetometers offer knobs for manual positioning of the sample in the correct position, but that procedure that is manual depends on the experience of the user and is a major source of uncertainty, which is very seldom smaller than 1%. A few systems, especially squids, offer an automated centering process that, in principle, should ease up repeatability. And most of the time this is true. Here you can see the signal coming from a squid magnetometer as a function of the position of the sample along the axis of the solenoid according to a certain reference. The signal shows a nice positive peak at a certain position, followed by two shoulders, negative shoulders, on the left and on the right. The system automatically fits this curve with a suitable model and identifies the position of the positive peak. That is the point where the sample must be placed, and it is placed automatically there in order to obtain the best measurements. The procedure works even for diamagnetic samples. The only difference is that the peak is negative and the two shoulder peaks on the left and on the right are positive. But the procedure works in the same way, so the system fits the curve with a suitable model and identifies the negative peak and uses that to determine the position of the sample. Except that you may not be that lucky. Here I show you two signals from the same squid magnetometers for a substrate of silicon and the other for a substrate of silicon oxide, where you can clearly see a lot of peaks, positive and negative, of similar intensity, and so it is very difficult to establish which peak is the correct one, which peak corresponds to the correct position of the sample. With signals of this kind, the automatic procedure of the instrument fails and is not able to establish the correct position of the sample. Why is all of this so important? Because, as you remember, when you want to obtain the magnetic moment of the sample, you must subtract several contributions of the holder, of the support, etc. And if you are not able to do a proper centering, for example, of the clean substrate, you are not going to measure the curve that you need to subtract to the total magnetic moment in order to obtain the magnetic moment of the sample. So even if the automatic centering procedure fails, you can still try to use an educated guess to see whether you can manually center the sample in a position that seems adequate according to one of the peaks of the signal that you see. But unfortunately, they may not be so trivial. Here in the graph, you see three measurements of a silicon substrate as a function of field in three different positions. Indeed, these are two different positions, but one is repeated two times, once with automatic centering and the other one with manual centering nominally in the same position. And the third time it is at a relatively different position. As you can see, the three slopes are very different, especially for the two repeated measurements. One is negative and the other is positive. So if you need to use that slope in order to compensate for the paramagnetic or diamagnetic effect of the support, of the substrate, of the holder, whatever, you are going to be in big trouble because you really do not know what you must subtract to the total magnetic moment in order to obtain the sample magnetic moment. You have a similar problem concerning the sample size. The sample shouldn't be too big, because the size of the sample affects the accuracy of the measurement of the magnetic moment. And in principle, and that is really hard to obtain, the calibrant should have the same shape and size of the sample. In the graph, you see how the measured magnetic moment changes if you misplace the sample with respect to the proper positioning across a radial coordinate in a solenoid, usually the solenoid of a squid magnetometer. As you can see, the relative variation can be extremely large. Here's a summary of the effects of a sample that is not placed in the proper position in the magnetometer, and also of the effects of a sample that has a shape that does not match the one of the calibrant. As you can see, properly centering the sample is probably the most important source of uncertainty when doing measurements with such magnetometers, and must be done with great care. Even if the rods to hold the samples in the magnetometers are uh, given by the manufacturers with their magnetometers, they are worth a discussion because every interface generates a magnetic pole that is measured by the magnetometer. What is an interface? For example, the interface between the rod and the sample, or the interface between the region where you put the PTFE tape to hold the sample in place and the region where the PTFE tape is no longer, ribbon is no longer present. So ideally, sample holders, rods, whatever you use to keep the sample in place should be passed through. So if you have coils or if you have a magnet with a pickup coils on the side, the rods must be as depicted in the two schemes in the slide. In case you wondered, the reason why the squid magnetometer was not able to properly identify the sample position for the silicon and silicon dioxide samples is that because there were interfaces present that whose magnetic moment measured by the squid was too close to that of the substrate itself, and so they were contributing signal that were almost of the same amplitude, and that prevented the algorithm to properly identify the main peak. So far, we have treated the magnetic moment measured by the magnetometer as a scalar quantity, but as you know, it is a vector. The trick is that the magnetometers measure the component of the magnetic moment parallel to the direction of the applied magnetic field. So, since they measure one component, that is a scalar quantity. But some magnetometers, normally VSMs, because for AGFMs it's not so obvious, you can add a second set of pickup coils to measure at least two components of the magnetization vector along two orthogonal directions. While in principle nothing prevents you from using three sets of coils to measure the three components of the magnetic moment, the design would become really cumbersome. So normally VSMs use 8 coil setups with 4 coils measuring the magnetization along the x direction and 4 coils measuring the magnetic moment along the y direction, whereas the z direction is left free for the sample vibration. The magnetic moment that you measure along the y direction does not look like a normal hysteresis loop. Indeed, it looks more like a sort of star. Okay? That is because the direction of application of the magnetic field induces a preferential direction along which the magnetic moment will lie during the application of the field itself. So it means that when you are approaching saturation, the x component of the magnetic moment will reach saturation, and the y component will go to zero. Conversely, when you go towards the coercivity, the x component of the magnetic moment will go to zero, and the y component of the magnetic moment can do a lot of different things. Typically, the magnetic moment reorients somehow along a certain direction that is no longer affected by the applied field, and that is the local anisotropy direction, which, if it does not coincide with the applied direction of the magnetic field, means that you have a value of my that is different from 0. As you may have guessed, if you can combine the possibility to measure the x and y components of the magnetization or of the magnetic moment with the possibility of rotating the sample inside the magnet gap, so by changing its orientation with respect to the applied field, you have a powerful tool to study the magnetization reversal processes in samples displaying a certain magnetic anisotropy. You can even exploit such an approach to do torque measurements that are meant for measuring the K1 component of the magnetic anisotropy. Let's go back to the problem of measuring the magnetic field, and let's briefly discuss what it means to measure a zero magnetic field. The field, if you have a means of measuring that, it is usually measured through a Hall probe along one axis, and so you have a feedback loop that compensates uh, the field generated by the magnet to the best of what the equipment can do. And usually you have a zero field state that is below 1 Ørsted, so let's say below 100 ampere per meter. Of course, with Helmholtz coils it is easier because if the current flowing in the coils is zero, then the field is zero, apart from the Earth's magnetic field. So if you want to shield from external fields, for example the Earth magnetic field, you must figure out a way to do that. Why? Because any magnetic material that you put in proximity of your magnetometer affects also the measurement. See, for example, the discussion of the image effect that we had earlier. Unless you use a very large shielding, so maybe a shielded room, which is built, which contains everything. So it means also the whole magnetometer. Even if you are able to do that, you still have the problem with the superconducting solenoids because, as we have seen, a zero current generated by the power supply does not mean a zero field, as there can be trapped flux. What can you do in order to zero the magnetic field generated by a superconducting solenoid? You have basically two ways. One is to use a special procedure, a sort of demagnetizing procedure, where you apply oscillating fields of progressively reduced amplitude. And the result is usually capable of doing a residual field that is better than 5 Ørsted. Unfortunately, this residual field can be still too high when you want to do specific sets of measurements, especially on magnetic particles. These measurements are called zero-field cooled measurements, for example. So, if you really need to go to a much lower field value of nominal zero field value, your best option is to quench the magnet. But in that case, it means that you are going to waste a lot of liquid helium. Unless you want to invest money into some accessories. For example, some superconducting solenoids can be equipped with a so-called ultra-low field accessory that is normally a flux gate magnetometer, a flux gate sensor that is capable of measuring the trapped flux that is in the superconducting coil, and so the system can apply a current of proper intensity in order to compensate for that trapped flux. The result is a zero field that is much, much smaller than what you can obtain by simply demagnetizing the superconducting solenoid. That accessory can turn out to be extremely useful when you need to do measurements at the best zero field that you can. This is typical for zero field cooled curves on superparc magnetic particles or diluted magnetic semiconductors, but also when you want to measure certain phase transitions like the Verwey transition in magnetite that are destroyed by an applied magnetic field, even a residual magnetic field. Of course, there are lots of different accessories for the magnetometers. Typical accessories include AC susceptometers, especially for squids, or cryostats or furnaces for VSMs and AGFMs. Furnaces, which are normally applicable mostly to VSMs, can go to temperatures up to approximately 1000 degrees Celsius. They are extremely useful for measuring phase transitions in metastable magnetic materials and Curie temperatures. Other very useful accessories include the automatic sample rotation and the vector options for doing anisotropy measurements, as we discussed earlier. Of course, there are a lot of other things that we could have said concerning static magnetometers, and that we have skipped for reason of time. For example, a very interesting topic is how to measure the magnetic moment in liquids, which is not trivial at all. Another class of magnetometers are pulsed field magnetometers that allow measurements only in transients but are able to apply very intense magnetic fields. Another problem is the control of the magnetic field, where you can have overshoot. Since you have a feedback loop and you want to reach a certain value, which could even be zero, then you must be sure whether you reach that field in a monotonous way or in a non-monotonous way. And even the time that it takes to reach the desired field value can affect the results of your measurement, because there are relaxation effects in the material that can be affected by such time constants. Another class of magnetometers are spinning magnetometers that are used especially in rock magnetism and geology to study the remnant state of materials, and a lot of other things that we did not have time to cover in this presentation. If you want to investigate in more details this subject, of course the literature is immense. Besides the application notes and usual manuals of the instruments of the magnetometers, a very good reference book is the first one reported here by Fausto Fiorillo. Thank you very much. You can find this presentation and all the other training material on the website of the TRaMM project. Thank you very much.